Alright, I'm going to be doing a problem straight out of this textbook. I've never used it before, but it's where the problem's from, so let's get into it. Alright, the problem says a Carnot engine between two finite heat reservoirs of total heat capacity, this one for the hot one, this one for the cold one. Develop an expression relating Tc to Th at any time. Determine an expression for the work obtained as a function of these variables and the initial temperatures. What is the maximum work obtainable, which corresponds to infinite time when the reservoirs obtain the same temperature. And it asks us to solve the problem using these equations right here. And before we get started, I want to say a few words on Carnot engine. So a Carnot engine takes in heat from a reservoir and rejects heat to a cold reservoir, producing work in the process, and usually follows four reversible steps. So in step 1, a system at an initial temperature of a cold reservoir at Tc undergoes a reversible adiabatic process that causes its temperature to rise to that of a hot reservoir at Th. So how do you get an increase in temperature despite being adiabatic? You basically compress the system. So if it's like a piston, just compress it. And then step 2, the system maintains contact with the hot reservoir at Th and undergoes a reversible isothermal process during which heat QH is absorbed from the hot reservoir. So how do you stay isothermal despite absorbing QH? Basically, you just expand. And yeah, you can read the other two steps, they're the same, just the opposite of that. But an overall assessment of that is that unless the hot and cold reservoirs are infinitely large or have infinite heat capacity, they will eventually reach the same temperature, which corresponds to when the maximum work is obtained. So solution for part A, it asks us to develop an expression relating Tc to Th at any time. So firstly, we can start by getting equations that involve Tc or Th somehow. And I'm just going to start by doing the formal energy balance on the hot reservoir. So I'm going to make the reasonable assumptions that kinetic energy and potential energy are negligible. And there's also no input stream or output stream, so these two terms go to 0. And then there's also no shaft work, and the volume of the reservoir isn't changing, so these two terms are also 0. So the energy balance then reduces to this. And I'm going to put a negative on front of this Q.H because from the perspective of the hot reservoir, it's giving it off, so it's losing, and it's like a decrease in internal energy. And then I can make these substitutions, and then this is equivalent to total internal energy. So this is what I get, and then that means that these differentials must be equivalent. I'm using this sign convention right here, which we're going to have to change because the textbook uses a different convention, which says that, note that QC with respect to the engine is a negative number, whereas QH is positive. So that means that with respect to the engine, if QC is a negative number, QC must be positive for the cold reservoir, and if QH is positive, then for the hot reservoir, QH must be negative, which means that here it is already readily negative, so I can get rid of that negative sign, and then this will be compatible with the equations that are given in the problem statement. So you can do a similar energy balance for the cold reservoir and get this statement between the differentials using this sign convention. And then if I go to the definition of changing internal energy in TV space, since volume is constant, I know dV is 0, so I can just ignore this term. And then I can use this relationship to then solve for CV, because it's just equivalent to that, so I just substitute in CV instead, and then I get change in molar internal energy is equal to CV dt. And then I'm given the heat capacities in the problem statement, and they're also given as constants, so that's pretty nice. And then I can say that du, the change in total internal energy, is equal to this, and then that must also equal this based off the relationship we found up here. And then same thing follows for the cold reservoir. And this might look a little weird, but it actually works out because CTH has units of joules per Kelvin. And then I can substitute these into the Carnot equation that's given in the problem statement now that I've solved for these different differentials. and then I can do some rearranging until these two terms are both on the same side, and then I can recall this relationship and I can apply it here, and I can make some substitutions, and then to make it nice I can define that gamma is equal to these two constants over each other, and then from here I can just integrate both sides and take the exponential and get this relationship, which gives Tc in terms of Th, which the problem asks for. In part B, determine an expression for the work obtained as a function of variables and the initial temperatures. So I can use the equation given the problem statement, I think the energy differential, is it called? Differential energy balance for the engine. I can then use that to rearrange and solve for dW, and then I can make these substitutions based off of the relationships we derived up here. You can make those substitutions, and then you just integrate both sides, and then you can find the work equals this, and then just pull more stuff out until you get this over this. And we know that based off from part A that these two are equivalent, as shown up here. From right here. So those two are equivalent, so I could just make that substitution in, and then that's how we eliminate Tc from our equation as the problem asked for. And now for part C, what is the maximum work obtainable? And this corresponds to infinite time when the reservoirs obtain the same temperature. So that basically means that all these three are equal. And I can go back to from what we found in part A, and the goal of all of that will basically be to eliminate, to find something of Th over Th naught, but while you do that, also eliminate Tc, so that the final equation we find will only rely on all the constants we defined at the beginning, so like Cth and the initial temperature, initial cold temperature. But yeah, pretty much just make all these substitutions as shown, and they're all pretty clarified here, and just make the substitutions into here, and you'll get that the work equals this equation right here. So that's the problem. Thank you.